You hit deploy, right, and the marketing campaign goes live.
Oh yeah, the best feeling.
It is. You check your analytics dashboard,
Yeah.
and the numbers are just climbing. Real users are actually flooding into this, this brilliant AI-generated SaaS application that you just built.
Right.
And for about 3 seconds, you feel like the absolute smartest person in the room.
Invincible.
Exactly. But then the dashboard just freezes, the login portal hangs, you're frantically refreshing the page, and there it is, the dreaded 502 bad gateway error.
Oh man.
The entire system has just spontaneously flatlined. Like the code that hummed so beautifully on your local machine yesterday has instantly collapsed in the real world.
It is, it's a uniquely modern kind of heartbreak, I think, and it's happening constantly right now. Oh, all the time.
Yeah.
Because the barrier to generating functional logic has dropped to near zero, right? Thanks to LLMs. But a lot of developers are colliding with this very harsh reality.
Which is what exactly?
Well, writing logic that works for, say, one concurrent user,
Right.
that is essentially a puzzle. You find the syntax, you solve the puzzle, the feature works.
Right, you get the output you wanted.
Exactly. But scaling that system to handle 10,000 concurrent users, that is no longer a puzzle. That is civil engineering. I mean, it's traffic management. It's fluid dynamics.
That makes total sense.
Yeah.
I was actually thinking about this while digging through our source material for this deep dive.
Yeah.
Building an app with an LLM without understanding back-end architecture, it's kind of like engineering the most aerodynamically perfect paper airplane the world has ever seen.
Okay, I like this.
Right? Like it glides gracefully across your living room. It's flawless.
Yeah.
But then you take that paper airplane, you walk outside, and you try to fly it in a Category 5 hurricane.
Yeah, that's a great way to put it, because the structural integrity required for those two environments couldn't be more different. Your crisp folds, they just don't matter when you introduce 150-mile-per-hour crosswinds. When you have one user, your server's CPU and its memory pool, they have all the time in the world to cater to that specific thread. But when 10,000 requests hit your server at the exact same millisecond,
Total chaos.
complete chaos. You introduce connection pool exhaustion, memory heap limits, network I/O bottlenecks. It's an entirely different physics engine.
Which brings us to the core mission of today's deep dive. We are going to deconstruct the physics of that hurricane.
I'm ready.
And the sources we are working from, they tackle this exact evolution of back-end architecture. But to keep us grounded, because, we could easily get lost in dry white papers about distributed consensus protocols.
Which nobody wants to listen to for an hour.
Exactly. So the sources map this entire journey to a highly practical narrative. We're going to trace the scaling of a fictional tech empire by looking at a humble storefront.
Ding Ding's bubble tea.
Ding Ding's bubble tea. We're going to build a boba empire.
I genuinely appreciate that the source material uses a physical supply chain analogy. Because data packets, they behave remarkably like physical inventory when they are routed under high concurrency.
They really do.
Yeah.
So let's start at the beginning. Where does Ding Ding's operation begin?
So we start at the absolute baseline.
Ground zero.
Right. Ding Ding's grandfather runs a tea farm up in the mountains, and after the harvest, there are leftover high-quality leaves.
Okay.
So Ding Ding takes this excess inventory, moves down to the bottom of the mountain, and opens a tiny bare-bones storefront.
Very scrappy.
Super scrappy. He's got a counter in the front, a messy warehouse in the back with shelves of tea, and a fridge for milk and tapioca. And Ding Ding is a solo operation.
He's doing everything.
Everything. A customer walks in, he takes the order, physically turns around, runs to the warehouse, finds the ingredients, brews the tea, and hands it over. Cashier, runner, barista, he is the entire stack.
So if we overlay our tech architecture onto this, what are we looking at?
We are looking at the classic monolithic single server setup. The counter where the order is placed, that's your front-end interface. Ding Ding, processing the logic of the order and executing the steps. He's your back-end runtime.
And the warehouse is the database.
Exactly. The warehouse storing the physical inventory is your database. In this initial stage, the front-end, back-end, and database are all sitting on one shared physical machine.
So this is like your standard $5 a month virtual private server.
Yeah, exactly. running a local node process and a local Postgres instance all in the same box.
The beauty of it is the lack of network latency, right? I mean,
Yeah.
Ding Ding doesn't have to call someone across town to get the tea. He just walks to the back room.
Right, the data doesn't have to travel over an external network interface. It's incredibly fast for one person.
Right.
But the vulnerability here is glaring. This is a massive single point of failure.
Right. Because if Ding Ding sprains his ankle, the entire business halts.
Exactly. In our architecture, if the node process happens to spike the CPU, or if, say, a rogue query eats up all the RAM, the operating system might panic.
Oh, and then it just kills the database process to save itself.
Yep, out-of-memory killer kicks in. Because they share the same finite pool of hardware resources, a failure in one component instantly takes down the entire application.
Wow. So the system is fragile.
Yeah.
But let's say the tea is phenomenal, right? So Ding Ding survives the early days. Word of mouth spreads. And this triggers our first real bottleneck.
The pain of popularity.
The pain of popularity. The line starts wrapping around the block. What used to be a 3-minute transaction turns into a 30-minute wait. Ding Ding is sprinting back and forth to the warehouse, red in the face, maxing out his physical output.
He's hit his limit.
Right. He cannot move any faster.
So in tech terms, the server is experiencing CPU throttling. The incoming request rate has exceeded the processor's ability to execute the application logic.
So this is when you're staring at a spinning loading wheel.
Exactly. The users are sitting there staring at a spinning loader because their HTTP requests are just queuing up. They're waiting for Ding Ding to finish the previous transaction.
So Ding Ding's instinct here is to upgrade his capacity. He hires his friends. He puts Sister 2 exclusively on the counter, taking orders. And Brother Hao becomes a dedicated runner to the warehouse.
It makes sense.
Yeah, he has essentially swapped out his own physical limitations for a team with far more muscle and speed.
Right, and translating that to our architecture, Ding Ding just executed a vertical scaling maneuver.
Vertical scaling. Scaling up.
Scaling up, yeah. Instead of rewriting his business model, he simply provisioned a much larger machine. If the application is choking, you log into AWS or GCP and you swap your modest little server for an instance with 64 CPU cores and 256 gigabytes of RAM.
You just give it a bigger brain.
You give the server a massive brain and massive temporary memory to hold all those concurrent tasks.
I mean, it sounds incredibly tempting. If I have a memory leak or an inefficient loop in my code, why spend 3 weeks refactoring it when I could just throw a credit card at the problem and double the RAM in 5 minutes?
And honestly, throwing compute at the problem is usually the most rational first step for a fast-moving startup. Oh, yeah. Developer time is expensive. Server time is relatively cheap, at least at first. But the physics and the economics, they eventually catch up with you.
Also,
First, you hit the physical hardware ceiling. There is a hard limit to the size of a motherboard you can rent. You can't just rent an infinitely large computer.
right.
But long before you hit the physical limit, the financial reality crushes you. Vertical scaling costs do not scale linearly. Moving from a mid-tier server to an enterprise-grade super server often results in an exponential jump in your monthly bill.
And that actually ties right into the utilization problem the source material emphasizes.
Yes, exactly.
Because Ding Ding's tea shop isn't slammed 24/7. They get a massive rush at lunch and another one the local schools let out. But at 10 in the morning, the shop is completely dead.
And that is the fatal flaw of vertical scaling as a permanent strategy. If you provision a massive instance to handle your noon peak, you are paying that premium enterprise rate around the clock. At 10 a.m., 90% of your CPU cycles and your memory pool are sitting completely idle. You are burning venture capital to keep Sister 2 and Brother Hao standing around, staring at the wall.
So the brute force strategy has a ceiling, both physically and financially. Ding Ding realizes that hiring 10 more people to run back and forth is just going to obliterate his margins.
He has to get smarter.
Right. You have to change how the work is done, not just how much muscle he throws at it. And this forces him to stop looking at the storefront and start investigating the warehouse.
So the bottleneck has migrated. It's moved from the application logic to the data retrieval layer.
Exactly. Ding Ding watches Brother Hao go into the warehouse to fetch a specific oolong tea. And the warehouse is a disaster.
Just boxes everywhere.
Total chaos. Inventory is just thrown wherever there was open space. Green tea is buried behind cleaning supplies. Tapioca pearls are scattered across 3 different unlabeled bins. Brother Howe spends 5 minutes just digging through boxes to find the right item.
This perfectly illustrates what happens when developers rapidly prototype an application and just stream data into a relational database without designing an efficient schema.
Just dumping it in.
Yeah, the data is securely stored, but it is effectively a black box.
So Ding Ding shuts the shop down for a weekend and fundamentally restructures the physical space. He implements a rigorous organizational system. Oolong teas are mapped to aisle 1, shelf A syrups are alphabetized in aisle 2.
Nice.
And, crucially, he creates a master ledger at the door. Now, when an order comes in, Brother Home checks the ledger, walks directly to the exact Cartesian coordinate of the item, and grabs it instantly.
That master ledger is the implementation of database indexing.
Okay, indexing.
And it is arguably the most critical optimization a developer can make before attempting any complex architectural shifts. When a database is small, say a few hundred users, a messy warehouse is totally fine.
Right, because Brother Howe can just scan the whole room in a second.
Exactly. In a database, if you ask it to find a specific email address without an index, it performs what's called a full table scan. It literally reads every single row in the table sequentially until it finds a match. With 100 rows, that takes microseconds.
But when that KOL influencer hits and you suddenly have 2 million users in the database,
Yeah.
reading 2 million rows sequentially for every single login attempt is going to spike your CPU to 100% and crash the database.
Completely. A full table scan on a massive dataset locks up the disk I/O. So indexing solves this by creating a secondary data structure, usually a B tree.
A B tree.
Right. When you tell the database to index the email column, it creates this highly optimized sorted tree pointing to the physical location of the data on the disk. So instead of scanning 2 million rows, the database traverses the B tree in logarithmic time O of log n, finding the exact hard drive sector in maybe 3 or 4 jumps.
That is a massive difference.
Oh, it's night and day.
Now, the source material also points out 2 massive self-inflicted wounds developers make at this stage. And the first is the select star habit.
Ah, yes, the asterisk. The asterisk is a wildcard, meaning return all columns. And developers often use it out of sheer laziness. I mean, we've all done it.
It's just faster to type.
It is. But if your front end only needs to render the user's display name and avatar, but your back end executes select from users, you are forcing the database to read, package, and transmit the user's password hash, their 10,000-word bio, their settings JSON, and their creation timestamp.
Wow. It's the equivalent of Brother Hal dragging the entire refrigerator to the front counter, grabbing the milk, and dragging the whole thing back, instead of just pouring a glass.
That is a perfect analogy. It's an absurd waste of network bandwidth between the database and the application server.
Just moving dead weight.
Right. And the memory allocation alone is disastrous. The back-end language has to deserialize all that useless data into memory objects before eventually throwing them away.
So what's the second trap?
The second trap the source details is the N+1 query problem, which is rampant when developers rely heavily on ORM's object relational mappers without checking the underlying SQL they generate.
Break down the mechanics of that. Why is it called N+1?
Okay, let's say your app is displaying a list of 50 recent purchases. And for each purchase, you need to show the name of the user who bought it.
Okay, simple enough.
A naive ORM setup will execute one query to fetch the 50 purchases. That's the one.
Got it.
Then, as it loops through those 50 purchases to render the web page, it fires a separate individual query to the database to fetch the user data for each one.
Oh, no.
That's the N. So for simple list of 50 items, your application is making 51 separate network trips to the database.
That sounds horribly inefficient.
It is, because network trips are expensive. Even if the query executes in 1 millisecond, the TCP/IP overhead, the connection pooling, and the data transit across the internal network adds up. A page that should load in 20 milliseconds suddenly takes a full second.
So how do you fix it?
The solution is writing a unified join query to fetch the purchases and the associated users in a single bulk trip. And the source wisely notes that this is exactly where LLMs excel in modern development.
Really? Like, you can just ask it?
Yeah, you can dump your schema and your slow ORM queries into an AI and ask it to audit for missing indexes and N+1 anti-patterns. It will spot them instantly.
That's incredibly practical. Okay, so Ding Ding has the warehouse perfectly indexed, the full table scans are gone, Brother Who can find the exact location of any ingredient in seconds, But Ding Ding is looking at the stopwatch, and he realizes he's still fighting the laws of physics.
Physical distance.
Exactly. Even knowing exactly where the tea is, physically walking the 30 feet from the counter to the back warehouse and back takes time.
Right. In our system, the disk latency still exists. Solid-state drives are fast, but they are not instantaneous.
So Ding Ding implements a brilliantly pragmatic solution. He buys a massive insulated bucket and an ice chest, and he mounts them right next to the cash register on the front counter.
I love this part.
Before the lunch rush, he brews a giant batch of his signature black tea and fills the insulated bucket. He puts the standard tapioca pearls in the ice chest. Now, when the inevitable wave of customers orders the standard boba, Sister 2 doesn't even talk to Brother Hao.
She bypasses the warehouse entirely?
She doesn't access it at all. She just pulls the lever on the bucket right next to her, seals the cup, and the transaction is done in 2 seconds.
Ding Ding has just introduced an in-memory caching layer. This is the architectural equivalent of standing up a Redis or Memcached server directly between your application and your main database.
Okay, wait, let me ask a dumb question. Why is memory so much faster than the database? The database is running on RAM too, isn't it?
It's not a dumb question at all. The database does use RAM for its own operations, but its primary job, its core directive is durability.
Meaning it can't lose the data.
Exactly. When a database commits a record, it must write it to the physical disk to ensure it survives a power failure. Disk I/O, even on NVMe drives, is orders of magnitude slower than accessing data directly from system memory.
So the cache just skips the disk.
A cache bypasses the disk entirely. It stores frequently accessed data, like, say, the compiled HTML of a trending news article or a user session token, as simple key-value pairs entirely in RAM.
But the insulated bucket analogy raises a very obvious red flag here.
Oh, I know where you're going.
If Ding Ding brews a batch of tea and leaves it in that bucket for 8 hours, it's going to get stale. The temperature drops, the flavor degrades, the data gets old.
Yes. You've just walked right into what is famously joked about as one of the 2 hardest problems in computer science.
What are they?
Cache invalidation and naming things.
Well, that's good.
But seriously, storing data in memory is trivial. Knowing exactly when to delete that data because the underlying source of truth has changed is a monumental engineering challenge.
Let's ground that in a real-world application so I can picture it. If I cache a user's profile page to make it load in 10 milliseconds, but then the user uploads a new profile picture to the database, my cache is now serving a stale, outdated image to the rest of the network.
Exactly. And how you solve that depends entirely on your business requirements. The simplest method is time to live, or TTL.
TTL?
Yeah. You tell the cache, hold this profile page for 5 minutes, then throw it away. If the user updates their picture, they might see the old one for up to 5 minutes. For a social media avatar, that eventual consistency is perfectly acceptable.
Nobody dies if an avatar is 5 minutes old.
Right. But for an e-commerce checkout showing available inventory, a 5-minute delay means you just sold the same pair of shoes to 6 different people.
Oh, wow. Yeah, that's a disaster.
Yeah.
So what do you do there?
In those high-stakes scenarios, you have to move to a right-through or right-behind clashing strategy. The application logic has to be sophisticated enough to say, when a purchase occurs, update the main database, and immediately send an invalidation signal to the Redis cluster to purge that specific inventory key.
That sounds complicated.
Very. It creates race conditions and complex distributed systems problems. But when implemented correctly, caching protects your fragile database from the vast majority of repetitive read traffic.
All right, so Ding Ding has maxed out the efficiency of his single location. The hardware is beefed up, the data is indexed, the heavy reads are cached. He is a local legend, and this pushes him into a completely new paradigm.
Oh, boy.
Ding Ding decides to franchise.
The leap from a monolith to distributed systems, this is where it gets real.
He brings in a professional corporate manager to execute the expansion, and Ding Ding assumes they will just find 50 new storefronts and perfectly clone his current highly optimized setup.
That's the natural instinct.
But the manager stops him immediately. The manager points out that having 50 independent stores, each managing its own separate warehouse, its own separate recipes, and its own local data, is going to result in absolute chaos.
Imagine the inconsistency.
Right. If they invent a new drink, they'd have to drive to 50 stores to teach the staff. Before they open store number 2, the manager forces Ding Ding to establish standard operating procedures, or SOPs.
The manager is enforcing statelessness and decoupling. You cannot horizontally scale an application if the application's state, meaning the data, the user sessions, the uploaded files, is permanently attached to the local file system of the compute instance.
So the first SOP the manager mandates is separation of concerns. Every franchise will have identical storefronts, but none of them will have a back warehouse. All the raw materials, all the master ledgers, and all the bulk insulated buckets will be centralized in massive, dedicated corporate facilities.
The physical uncoupling of the monolith. In AWS terms, you are stripping the database off the EC2 instance and moving it to a managed service like RDS. You pull the Redis cache off the local host and move it to Elasticache.
Okay.
And critically, you stop saving user uploads like profile pictures or PDF receipts to the server's local hard drive. You route all of those static files to an object storage bucket like S3.
Why is the file storage separation so critical? I feel like people overlook that.
They do, constantly. Imagine your monolithic app saves a user's uploaded avatar to the Varbo Loploans folder on server A. Tomorrow, you scale up and add server B. When that user logs in again, the load balancer routes them to server B.
And server B doesn't have the file.
Exactly. Server B looks in its local uploads folder, finds nothing, and the user's avatar is rendered as a broken image link. By moving files to S3 and the database to RDS, you render the application servers completely stateless.
Meaning what, exactly?
Meaning server A and server B are essentially identical blank processing engines pointing to the same external brain. You can destroy one and the system doesn't lose any data.
Which perfectly sets up the manager's second SOP, standardized environments.
Right.
The manager demands that every franchise kitchen must be constructed using exact prefabricated modular units. The counters must be exactly 36 inches high. The blenders must be the exact same wattage.
Consistency is everything here.
Exactly, because this guarantees that a barista trained at store number 1 can walk into store number 49 and instantly know how to operate the machinery without retraining.
This is the philosophy behind containerization, and Docker is the industry standard for it. The era of a developer saying, well, it works on my machine, that ended with Docker.
Such a classic developer excuse.
It was, because before containers, deploying code meant wrestling with the server's host operating system. Your local Mac might run Python 3.0, but the production Ubuntu server is running 3.8. The dependency trees conflict, and the app crashes on deployment.
But wait, I thought virtual machines solved that. Like you just spin up a whole virtual computer on the server.
VMs do solve the isolation problem, absolutely, but they are incredibly heavy. A virtual machine requires booting up an entire guest operating system, a full copy of Windows or Linux, just to run a small app.
So it's overkill.
Massive overkill. It consumes massive amounts of RAM and takes minutes to boot. Docker containers, on the other hand, share the host system's kernel. They use Linux groups and namespaces to isolate the application process, its specific libraries, and its dependencies into a lightweight, portable package.
So this container holds just what the app needs to run, and literally nothing more.
Exactly. And because it's so lightweight, it spins up in milliseconds. You build the Docker image once on your laptop, and you guarantee it will execute identically on an AWS ECS cluster, a Google Cloud Run instance, or a Raspberry Pi in your closet.
The third SOP the manager implements handles updates. When Ding Ding invents a new seasonal mango tea, he can't have managers driving the recipe card to 500 different stores.
The potential for human error is just too high. Someone transcribing the recipe wrong or a card getting lost.
Right, so he establishes a central dispatch system. Ding Ding finalizes the recipe at headquarters, pushes a button, and the exact instructions are simultaneously transmitted to the digital displays in every franchise kitchen across the country.
This maps perfectly to the CI/CD pipeline continuous integration and continuous deployment.
CI/CD?
Yeah. When you have an infrastructure of 50 or 500 servers, you absolutely cannot rely on developers manually SSHing into servers to pull code from GitHub and restart services. It is a terrifying operational risk.
I imagine one missed keystroke just takes down a production node.
Oh, constantly. CI/CD automates the entire lifecycle. When a developer pushes code to the main branch, the CI server intercepts it. It automatically provisions a clean environment, runs the suite of unit and integration tests, and if and only if the tests pass, it builds the new Docker image.
So it's a safety net.
A huge one. And then the CD pipeline orchestrates the rollout. It might use a rolling update strategy, taking down 5 old containers and spinning up 5 new ones, gradually migrating the traffic without a single second of downtime. The entire process is codified, deterministic, and untouchable by human hands during execution.
The final SOP is automated surveillance. The manager installs health check cameras in every kitchen. If a blender catches fire, headquarters knows instantly and automatically reroutes orders to the store down the street while dispatching a repair team.
System telemetry. This is so vital. Load balancers constantly ping the health endpoint of every application container.
Like checking a pulse.
Exactly. If a container suffers a memory leak and stops responding with an HTTP 200 OK status within, say, a 2-second timeout, the load balancer ruthlessly stops sending traffic to it.
It just cuts it off.
Yep. The container orchestration tool, like Kubernetes or AWS autoscaling, sees the dead container, kills the process entirely, and automatically spins up a fresh replica to replace it.
Wow. So the foundation is absolutely rock solid now. Ding Ding has decentralized his state, he's containerized his logic, and automated his deployments.
He's ready.
He is ready for the empire phase.
Ugh.
Step 6, the clone army. Ding Ding aggressively expands, opening 500 identical storefronts across the region.
This marks the architectural shift from vertical scaling to horizontal scaling, scaling out instead of up. Rather than buying one multi-million-dollar mainframe, Ding Ding is leasing 500 cheap commodity servers.
Which raises an immediate logistical question. If I am a customer and I type dingdingt.com into my browser, how does the internet know which of those 500 stores to send me to? I'm not typing server-142.dingdingt.com.
You are routed to the unsung hero of distributed systems, the load balancer.
The traffic cop.
The ultimate traffic cop. The DNS record for your domain points to a single, highly available component at the edge of your network. The load balancer acts as a reverse proxy. It accepts the inbound HTTP connection from the user, inspects it, looks at its pool of 500 available backend servers, and makes a real-time routing decision.
What's the logic behind that decision, though? Is it just dealing cards left to right?
Actually, the simplest algorithm is exactly that. It's called round robin. Request 1 goes to server A, request 2 to server B, and so on.
Seems fair.
But round robin is dangerous if the workloads are uneven. If server A receives a request to export a massive CSV file, it might lock up its CPU for 10 seconds. If the load balancer blindly sends the next round robin request to server A while it's locked up, that user is going to suffer massive latency.
So the load balancer needs to be smarter than just a simple rotation.
It does. In production, you typically use a least connections or target tracking algorithm. The load balancer actively monitors the active TCP connections on every backend node and routes the new user to the server with the least current workload.
That makes a lot of sense.
And this ties directly into the autoscaling mechanics we touched on earlier. The orchestration layer watches the aggregate CPU and memory metrics across the entire fleet.
The elasticity of the cloud. This solves the 10 a.m. lull problem that bankrupted vertical scaling.
Precisely. You define a policy. If average CPU utilization exceeds 70% for 3 minutes, launch 10 new containers. If average CPU drops below 30% for 10 minutes, terminate 10 containers.
So with breathing.
Yes. The infrastructure expands and contracts organically matching the traffic curve, ensuring you never drop a request during a spike and you never pay for idle compute during a lull.
You know, you mentioned a phrase earlier, transitioning from treating servers like pets to treating them like cattle. I think that applies here.
It's the foundational mindset shift of cloud engineering. When you have a monolithic single server, it is a pet. You name it. If it gets a virus, you nurse it back to health. Its death is a catastrophe.
Right.
But in a horizontally scaled, stateless environment, servers are cattle. They are numbered, disposable compute units. If a node fails, you don't investigate or reboot it. You terminate it and let the autoscaler replace it.
Okay, so the 500 app servers are humming. But remember, they are all stateless. They all rely on the central corporate facilities for data. And this triggers the next massive bottleneck.
Here we go.
Ding Ding launches a nationwide loyalty app. Customers can scan their phones to earn points and get discounts. The problem: checking a point balance requires reading the central master ledger. At 12:30 p.m., all 500 stores are packed, and thousands of customers try to scan their apps simultaneously.
A massive read spike.
Exactly. 500 app servers instantly bombard the single central database with read queries. The database CPU spikes to 100%, the query queue fills up, and the entire nationwide network grinds to a halt.
The compute layer is horizontally scaled, but the data layer is still a monolith.
Right. So my immediate instinct, based on what we just learned, is to just auto-scale the database, put a load balancer in front of the database, and spin up 50 copies of it. Why doesn't that work?
Because of the nightmare of distributed consensus and state mutation.
Say more about that.
Let's use the physical ledger analogy. If you put 5 accountants at 5 desks, each with their own blank ledger book, and you put a load balancer in front of them, what happens?
Well, customer A deposits $100 with accountant 1. Customer B withdraws $50 with accountant 2.
And when customer A tries to check their balance an hour later, the load balancer routes them to accountant 3. Accountant 3 looks at their ledger, which is blank, and tells customer A they have $0.
Oh, wow. Yeah.
This is a massive violation of ACD compliance, atomicity, consistency, isolation, durability. If you have multiple master databases accepting writes independently, resolving the conflicts of who has the correct data is a computationally brutal task.
You essentially trigger a split-brain scenario where the system literally doesn't know what reality is.
Exactly.
So how do we relieve the pressure on the database without breaking reality?
We analyze the workload and execute a strategy called read-write splitting. If you analyze the traffic of almost any application, Twitter, Netflix, Ding-Ding's bubble tea, the ratio of reads to writes is incredibly skewed.
People read way more than they write.
Massively. Users look at their loyalty points, browse the menu, and read reviews 100 times for every one time they actually create a new order or update their password. Reading data does not mutate state. It does not cause consistency conflicts.
So you segregate the traffic based on intent.
Exactly. You designate your original database as the primary or master. It becomes the single source of truth, and its only job is to process incoming writes, new orders, new accounts. Then you provision multiple read replicas. These are exact copies of the primary database, but they are strictly read-only. You configure your application logic to route every single select query, the menu browsing, the point checking to the fleet of replicas. You have successfully scaled the read capacity horizontally.
But the replicas have to get the new data somehow, right?
Yeah.
If I sign up for an account on the primary, how do the replicas know I exist?
The primary database continuously streams its transaction logs, its bin logs, to the replicas over the internal network. The replicas ingest these logs and constantly replay the transactions to keep themselves updated.
That streaming process isn't instantaneous, though, is it? There has to be a physical delay.
And that delay introduces a concept every distributed systems architect must wrestle with: replication lag. Because the network takes time and the replica needs CPU time to write the update, there is a window, usually milliseconds, but under heavy load, potentially seconds, where the replica is out of sync with the primary.
Eventual consistency.
Eventual consistency, yes.
What happens if a user falls into that lag window? Let's say I update my username on my profile page, which writes to the primary. I hit submit, the page refreshes, and my app reads my profile data from a replica that hasn't caught up yet.
The user sees their old username and assumes the app is broken.
Which is a terrible user experience.
It is. So to mitigate this, developers use techniques like read after write consistency. The application logic remembers that you just performed a write, and for the next, say, 5 seconds, it forces all your read requests to go directly to the primary database.
Oh, bypassing the replicas entirely.
Exactly, ensuring you see your own updates immediately. It's an added layer of architectural complexity, but the trade-off for unblocking the database bottleneck is non-negotiable.
Okay, so the architecture is becoming a web of specialized components, which brings us to step 8, splitting the empire.
Microservices.
Yes. Ding Ding looks at his monolithic corporate structure. Managing the factory that roasts the raw tea leaves is a fundamentally different business than managing the marketing team that runs the mobile app. The processes are tangling together.
Too much friction.
Right. So he executes a massive corporate restructuring. He spins off Ding Ding Tea to exclusively handle raw materials and supply chain. He creates Ding Ding Bubble Tea to handle retail and user experience. The companies are independent. They have their own CEOs, their own payrolls, and they only communicate via formal invoices and contracts.
This is the death of the monolithic codebase and the birth of microservices.
Even if the monolith was horizontally scaled across 500 servers, the code itself was still one giant compiled executable, right?
That's the danger. In a monolith, the payment processing logic, the email notification system, and the image resizing algorithms are all compiled together, sharing the same memory heap and the same CPU threads.
And why is that bad?
It creates two massive problems. The first is organizational velocity. If a team of 100 developers is working on the same repository, pushing updates becomes a nightmare of merge conflicts and integration testing. The second problem is the blast radius of a failure.
Explain the blast radius.
Let's say a junior developer pushes a bug in the image resizing logic that causes an infinite loop. It maxes out the CPU. Because the entire application shares that CPU the payment processing module can't execute, The login module can't execute. A bug in a completely trivial feature takes down the core revenue-generating systems of the company.
Ouch. So microservices acts as a system of bulkheads in a submarine.
Precisely. You carve the monolith into small, autonomous services aligned around business capabilities. You create an auth service, an order service, an inventory service.
Okay.
Each service is its own code base, runs in its own isolated Docker containers, and critically, manages its own independent database. They communicate exclusively over the network, usually via REST APIs or asynchronous event buses like Kafka.
So the blast radius is contained. If the notification service crashes, users don't get their confirmation SMS, but the order service keeps processing credit cards and generating revenue.
Yes, and you gain the superpower of independent scaling. On Black Friday, your order service is getting hammered, so you scale it out to 200 containers. Your user profile service is barely being used, so you scale it down to 2 containers. You allocate compute resources with surgical precision.
The caveat, of course, is that you've just traded monolithic complexity for network complexity. Making 20 different databases stay in sync across HTTP calls sounds like a debugging nightmare.
It is the operational tax of microservices. You introduce network latency between functions that used to just be in-memory method calls. You have to implement distributed tracing tools like Jaeger or OpenTelemetry just to figure out which microservice in the chain caused the HTTP 500 error.
So don't do it right away.
The source is explicitly clear. Do not start with microservices. You evolve into them only when the organizational friction of the monolith outweighs the network tax of distributed systems.
Got it. Okay, we are entering the final phase. The empire is humming, but extreme viral edge cases test the boundaries of physics. Step 9, bringing content closer.
Okay, what's the scenario?
The Dragon Boat Festival is approaching. Ding Ding's marketing wing produces a gorgeous, high-definition promotional video and high-res PDF menus. Initially, they host all these massive files on their central server in Taipei.
I see where this is going.
What happens? Users all over the world try to download the video. The central server's outbound network bandwidth is instantly saturated. The pipe is completely clogged.
This is a network egress bottleneck. The compute isn't failing, the database is fine, but the physical fiber optic cables leaving your data center can only push so many gigabytes per second.
Right.
Furthermore, a user in New York requesting a 50 megabyte video from a server in Taipei is fighting the speed of light. Every packet has to cross the Pacific Ocean, introducing massive latency.
So Ding Jing physically intercepts the problem. Instead of forcing everyone to call headquarters, he prints thousands of posters and ships hard drives full of the video to every local branch worldwide.
Brilliant.
Now, a customer in New York doesn't connect to Taipei. They walk to the local franchise in Manhattan and watch the video locally.
You've just described a content delivery network, or CDN. A CDN is a globally distributed network of proxy servers, known as edge nodes.
Edge nodes.
Yeah. When you implement a CDN, you upload your heavy static assets, images, videos, compiled React JavaScript bundles to your origin server. The CDN provider, someone like Cloudflare, Fastly, or AWS CloudFront, pulls those assets and caches copies of them in hundreds of data centers around the world.
So when a user in New York visits the website, their DNS request is intercepted by the CDN via Anycast routing, and they are dynamically connected to a server sitting in a data center in Brooklyn.
Exactly. The video downloads instantly with zero latency. And crucially, it completely shields your origin servers from the bandwidth onslaught. Your expensive EC2 instances are no longer wasting CPU cycles serving static JPEGs. They are entirely focused on executing dynamic business logic.
Okay, the static assets are offloaded. But what about dynamic traffic spikes? This brings us to the final ultimate defense mechanism. Step 10, queues and rate limiting.
The big guns.
Ding Ding decides to run a Double 11 Singles Day promotion. A viral, massive flash sale. $1 boba, limited to the first 100 people at each store.
The quintessential stampede scenario.
It is the Taylor Swift Ticketmaster disaster. At exactly 11:00 a.m., thousands of people rush the doors of every single franchise. It is uncontrolled, concurrent chaos. People are trampling each other. The glass counter breaks, the cash registers jam, and the store is physically destroyed. Nobody gets tea.
Right, because a viral event requires writing state, checking out of a shopping cart, claiming a ticket, submitting an order. These are heavy transactional database writes.
And the database can't handle it.
We already established that the master database is the singular bottleneck for writes. A CDN can't cache a credit card transaction. A read replica can't process a new order. If 100,000 concurrent write requests hit your application layer, the app servers will attempt to open 100,000 concurrent TCP connections to the master database.
And the database just says no.
It runs out of available connection pools instantly. It locks rows to prevent double spending, deadlocks occur, memory is exhausted, and the database outright crashes. The entire application goes dark.
So to survive the stampede, Ding Ding changes the rules of engagement. He sets up a serpentine red velvet rope outside the store.
I like the velvet rope.
It works, right?
Yeah.
He puts a highly aggressive bouncer at the door. When 10,000 people rush the store, the bouncer uses a clicker. He lets exactly 5 people into the store. The other 9,995 people are forced to wait outside the door.
Okay.
The store environment remains calm. The barista makes the 5 drinks perfectly, and then the bouncer lets the next 5 in.
The bouncer is the rate limiter, and the velvet rope is the message queue. You must prioritize the survival of the database over the instant gratification of the user.
How does the rate limiter work in code?
A rate limiter is a gateway, often implemented via an API gateway or at the load balancer using a token bucket algorithm. It enforces strict concurrency rules. The checkout endpoint will only accept 5,000 requests per second. If request 5001 arrives, it is immediately dropped with an HTTP 429 too many request status.
But dropping a customer's request during a checkout is terrible for business. You lose the sale.
Which is why the rate limiter feeds into an asynchronous message broker, like AWS SQS, RabbitMQ, or a Redis stream.
The queue.
The queue. When the 100,000 users click buy, their request isn't sent to the database. The application wrapped their order data into a lightweight JSON message and drops it into the queue. The queue acts as a massive, highly durable shock absorber.
And what are the back-end application servers doing?
They are acting as asynchronous workers. They completely ignore the front-end traffic. They just look at the queue and say, I am configured to process 50 orders a second. They pull 50 messages off the queue, validate the inventory, charge the credit cards, write the results to the database, and then go back to the queue for the next batch.
So the database is protected.
The database is never overwhelmed because it dictates the pace of ingestion, completely divorced from the velocity of the front-end spike.
But the user experience changes dramatically here. In a normal HTTP request, the user clicks buy, the server processes it, and returns a success screen. If the request goes into a queue, the server doesn't know the result yet.
This is where front-end architecture has to adapt to back-end realities. The front end receives an immediate response saying, order accepted into queue, ID 12345. The UI then displays a spinning wheel or a progress bar and uses WebSockets or long polling to repeatedly ask the server, is order 12345 done yet?
You are currently in line. Please do not refresh this page.
Exactly. You are artificially degrading the user experience to ensure the structural integrity of the application. The system survives the hurricane by refusing to fight the wind directly.
We have taken Ding Ding from a single shed on the side of a mountain to a global, microservice-driven, auto-scaled, CDN-backed, asynchronously queued empire.
It's quite a journey.
And looking at this evolutionary map, the meta lesson is profound.
The lesson is that premature optimization is the root of all evil.
Yes.
If Ding Ding had attempted to build a multi-region Kafka event streaming architecture and a Kubernetes cluster when he was selling 3 cups of tea a day, he would have spent millions of dollars on infrastructure overhead and collapsed before he made a profit.
You scale when it hurts. Architecture is a reactive science. You build the simplest thing possible, you monitor the telemetry, you identify the exact bottleneck, and you apply the specific architectural pattern designed to relieve that pressure point.
And that brings us full circle to the person staring at their crashed AI-generated app.
Right back to the beginning.
LLMs are miraculous tools. You can ask Claude to write the YAML configuration for a Kubernetes cluster or generate the Python logic for a Redis token bucket rate limiter, and it will give you perfect deployable syntax. It lowers the barrier of execution to 0.
But the LLM is just a bricklayer. It lays bricks flawlessly and infinitely fast, but it cannot tell you where to build the wall. If your database is experiencing row-level locking deadlocks, and you just ask an AI to make my app faster, it might refactor your React frontend or implement a caching layer that completely fails to address the underlying data integrity bottleneck.
You have to know how to diagnose the system.
Yeah?
You have to understand the physics of distributed computing. You must know what connection pooling is, how indexing traverses a disk, and why synchronous writes fail under concurrency.
You have to be the architect.
Because only then can you tell the AI bricklayer exactly what structure needs to be built to save your system.
And that leaves us with a fascinating, slightly provocative thought to end on for everyone listening. As AI inevitably masters the actual syntactical writing of code, the sheer act of programming becomes a commodity.
It does.
Will the true value of a software engineer in the next decade lie entirely outside of the code editor? Will the developers of tomorrow evolve strictly into the city planners of these digital empires, spending their days analyzing traffic flow, defining blast radiuses, and orchestrating queues while the AI endlessly, tirelessly lays the bricks?
It forces us to ask whether we are currently training developers to be syntax experts or system thinkers.
It's a massive paradigm shift.
Yeah.
So the next time you launch that beautiful new app and the load screen freezes into oblivion, don't just blame the code. Take a step back, look at the telemetry, observe the hurricane, and ask yourself, where exactly is the bottleneck in the warehouse?